Hi, welcome to Gas Laws Part 3. My name is Dr. English, and today we're going to talk about Charles' Law. Specifically, we're going to introduce the concept of Charles' Law and look at the variables involved, look at graphing temperature versus volume, solving for temperature and volume, and then a little bit of practice at the end. So Charles' Law is a temperature and volume relationship. It states that if the pressure of a gas is held constant, the volume of the gas is directly proportional to its Kelvin temperature. And one of the key things that you need to remember here is that if you're given a problem whose temperature is in degrees Celsius, you want to convert that into Kelvin before you do anything. So if the Kelvin temperature is doubled, the volume must also double. And at the same time, if the Kelvin temperature is halved, the volume must be halved. So we have this volume and temperature constant right here, where we're going to see a direct relationship. So then this number K, which represents our constant, is the same for any two volume and temperature points. Graphing the pressure-volume relationship. Graphically, Charles' Law is shown as a straight line with a positive slope. This indicates that there is a direct relationship between volume and temperature. So what we see here as temperature in Kelvin increases, the volume will also increase directly. And again, one more time, the temperature must be in Kelvin when using Charles' Law. So make sure you look on table T if you've forgotten how to convert from Celsius to Kelvin. This animation shows the relationship between volume and temperature. Here you can see that temperature is being added to this gas, which is in a closed system. So as the temperature increases, the volume is also increasing. Now let's do an example where we're solving for temperature and volume. Using the combined gas law from reference table T, the variable of pressure can be removed. So we have this relationship right here on reference table T, and what we want to do is remove the pressure variable, and then we'll have our relationship between volume and temperature. So let's look at this example. A balloon has a volume of 3.5 liters at a temperature of 50 degrees Celsius. What would the volume of the balloon be if you take it out into the winter cold air at negative 15 degrees Celsius? The first thing that we want to do is convert our Celsius temperatures into Kelvin temperatures. So we're going to do 50 degrees Celsius plus 273. And if we add these two numbers together, we will get 323 Kelvin. Then we want to take negative 15 degrees Celsius and add 273. And when we add them together, we will get 258 Kelvin. Once we have those numbers, then we can write our formula. V1 over T1 is equal to V2 over T2, where our initial volume is 3.5 liters. So I'm going to plug that into my formula, 3.5 liters. My V2 is going to be 50 degrees Celsius, and we figured that was 323 Kelvin. That's equal to my V2, which is what I'm solving for here, and then my T2, which is 258 Kelvin. What I want to do here now is I want to cross multiply. So I'm going to do 3.5 liters times 258 Kelvin, and I'm going to set that equal to V2 times 323 Kelvin. So if I were to write this out, it would be 3.5 liters times 258 is equal to 323 times V2. So my V2 will equal 2.8 liters. Now let's again look at the relationship here. If my temperature is decreasing, like it is here, 323 Kelvin to 258 Kelvin, my volume should also be decreasing. So I have an original volume of 3.5 liters and an end volume of 2.8 liters. Therefore, my answer makes sense. Now what I want you to do is stop, see if you can attempt the next two practice problems, come back and check your work. Welcome back. Let's see how you did. A container of a gas has a volume of 5 liters at 70 degrees Celsius. If the container expands to 6 liters, what would the new temperature in the container be? So again, the first thing I'm going to do is convert this from 70 degrees Celsius by adding 273 into Kelvin. And if I do that, my answer will be 343 Kelvin. Then I'm going to set up my formula. V1 T1 is equal to V2 T2, where my volume, my initial volume, is 5 liters, and I found that that was 343 Kelvin, and my final volume is 6 liters, and I am solving for T2 here. Now, personally, I don't have a problem if you leave your answer in Kelvin. That's not a big issue. But if you're not one of my students, you might want to ask your teacher if your teacher wants you to convert your T2 here, which is in Kelvin, back into Celsius. So again, what I'm going to do here is cross multiply these two things together. So ultimately, I'll have 5 times T2 is equal to 6 times 343. I'm going to divide both sides by 5, and then my final temperature in Kelvin will be 411.6, and if I round that to 3 significant figures, it'll be 412 Kelvin. Now again, one more time, let's look at the relationship of what we had here. My volume was increasing, so again, my temperature should be increasing. So 343 to 412, I see an increase in temperature. My final answer makes sense. Let's go ahead and look at our final practice problem. You were given 25 liters of a gas at 100 Kelvin. What would the new temperature of the gas be if it was compressed to 10 liters? So the first thing that I'm going to do is write out my formula. V1, T1, V2, T2. My initial volume is 25 liters. My initial temperature is 100 Kelvin. My final volume is 10 liters because we are compressing it, and I am solving for my final temperature. So again, I'm going to cross multiply here. So it's going to be T2 times 25 and 10 times 100. So when I write this out, it'll be 25 times T2 is equal to 10 times 100, and I'm going to divide both sides by 25, and when I solve for my T2 here, my final answer will be 40 Kelvin. So again, let's look at our answer and see how it compares. So 25 liters to 10 liters, that means my volume is decreasing, therefore my temperature should also be decreasing. So 100 Kelvin to 40 Kelvin makes sense with my final answer. So what did you learn in this tutorial? We introduced the concept of Charles' law, we looked at a graph of temperature versus volume, we solved for temperature and volume, and then we did a little bit of practice at the end. Need more help? Feel free to contact me. Have a great day.